try some examples with root macros. So if you have nothing else to do but listening to my lecture and you have not installed the root yet, you can try to do so on your laptop if you have one, so that you will be able to follow better what we will be doing together later on. So 2 days ago, we stopped the discussion at more or less at this point. We were discussing the goodness of fit tests. And I was making the point in this slide that they don't require you to specify an alternative hypothesis. So you have some data and you have a model. Your null hypothesis, like H0 is all you have. And therefore, you can only get to know how compatible your data are to your model. So you will specify an alpha level, a type 1 error rate, and then you will accept the model or reject it based on the particular p-value that you get, whether it is smaller or not than alpha. So you will still have a critical region which allows you to reject the model or not, but you will not have a power measure, which is 1 minus beta, where beta is determined by the alternative hypothesis, which you don't have because you only have one model. And therefore, it doesn't make any sense to say which goodness of fit test is best for a given set of data or a given model, because it depends. Some tests will be more sensitive to some variations from the model you are trying to assess, and others will be more sensitive to other features. And I've made a few examples. Okay, so I wanted to pound on this issue just to then go to to discuss the 5 sigma criterion. So, and we also had this quote about Feynman that was joking, of course, about a posterioriness, the fact that if you don't define beforehand the region of interest of your tests, then you can find significant observations everywhere, okay? So this is another example where you have a Poisson with a mean of 100 events in a counting experiment, and you only observe 80. So if you are confronted with the question, how significant is that observation, that discrepancy from the expectation, which is the maximum likelihood expectation is 100 for a Poisson of mean 100. You have to first, you would have had to first define the region of interest as large values of n or small values of n. And the answer, of course, for the p-value changes. Or even you could imagine actually computing the probability of observing exactly 80 events. That is small, of course, but it doesn't answer anything really, right? Because it's just a random variable that takes on that value for a chance, by chance. So here I have an example of a Kolmogorov test that arises in historical analysis of the CDF experiment. And this you see on the top right is the rapidity of a charged lepton of high momentum in CDF data collected in run 1, so 25 years ago. And you had the data, which are here at the empty red histogram, and the model, which is the sum of blue and green. And here you can see that there was this observation that you were seeing these leptons at very high rapidity in the positive direction, or even if you want in the absolute value. And you were asking yourself how likely it is that I would see such an asymmetry in the primary lepton emission. Okay, you don't know, maybe some of you don't know what is rapidity. We are talking about proton-antiproton collisions here, and the leptons at the proton collider are very indicative probes of electroweak processes, and so are intrinsically interesting. But okay, the authors of this analysis, which was observing 13 events in a sample that should only contain 4.4 expected from Monte Carlo, they had this probability of observing 13 or more events, which you could compute by a tail probability for a Poisson, and that was 10 to the -3. In the tutorial, we are going to do this exact exercise, one of the exercises we'll do. But so they not only had a counting experiment, they also saw that they have several, I would say maybe 15 or 20 kinematical distributions that they could extract from the features of these events, that they were odd. They were discrepant not only in normalization, 13 versus 4.4, but also in shape, such as this primary lepton rapidity. So they did a Kolmogorov test on each of these variables. And the Kolmogorov, you see this in the bottom right, means to compare the cumulative distribution of the expected background and the data that you have, which are these points with uncertainty bar. And the maximum distance of these two distributions is an indication of, is a statistic with which you can get a p-value. And they did so, and they obtained a very small p-value. Before we see those results, just for fun, they had many p-values to compare to extract a global measurement of disagreement. So what do you do when you have many p-values from independent tests? So they are not correlated. Okay, you have to assume that they are not correlated, otherwise things get very difficult. But you can still try to answer the question. So I see some p-values that are small, okay? Can you actually cook up a summary of this set of p-values that tells you how strange they are, how small they are, or how peculiar it is that you get such a collection of numbers? And of course, the answer depends on the question that you're asking, right? So what is the probability that the smallest of them is as small as the one that I got? Or what is the probability that the largest one is as small as the largest that I observe? Or you could take the probability or the sum, or, you know, everything can be done, but they will all be different questions that you ask to the data, okay? So you cannot do this choice a posteriori, because you will fool yourself. But let's suppose anyways that you believe that each of these p-values carries information on discrimination of some new physics process from the standard model or something else. So you don't want to focus only on one of them, on the smallest maybe. You want to let all of them speak. So maybe one thing that you want to do, not optimal, because there is no optimal thing to do. As I said, in a goodness of fit test, you don't know what's the alternative hypothesis, so you cannot define optimality, but you can try to use the product of the n p-values. Now, the formula that provides the distribution of the product of that we call x here of n p-values is this one here. For the null hypothesis, that means to say that if you are multiplying p-values that are all numbers constructed to be between 0 and 1, and have a flat p-value, flat distribution between 0 and 1, you're going to get a small number as you multiply them, because, well, you take the typical value is a half, and if you multiply a half by itself 2, 3, 4 times, you get increasingly small results, right? So you can try to extract this distribution on the null hypothesis, that is, all of these p-values are drawn from a uniform in 0 to 1. And so you can compare this product to what you actually observe in the data. And so we can make an example here. You take 5 really uniformly distributed p-values. So the most uniform set that I can cook up is 0.1, 0.3, 0.5, 0.7, and 0.9, right? 5 values uniformly distributed. If you take their product, that's a little less than 1%. And using the formula, you get the p-value of this combination, of this product, and that's 50%. So the p-value of this combination using that product p-value test statistic is 50%. So it is it feels good that you are getting a non-controversial answer, right? A number which is very common. Well, as any other number between 0 and 1. But now suppose that instead one of these 5 numbers was very small. Suppose that x1 is 10 to the minus 5. The product of these 5 numbers, where we have only modified the first, is 10 to the minus 6. And the probability, given that the formula that we already said, is 10 to the minus 3. So what this tells you is that when only one of the 5 numbers is very small, and you have chosen to look at the product of the 5 numbers, well, this smallness of the one of them gets washed away a little bit. So you don't get a 10 to the minus 5 probability for the product, you get a larger probability. Then this also makes sense. Now, another example, if you let all of the 5 numbers be uniformly distributed between 0 and 0.3, something like that, so they are all small now, their product is also smallish, but not compellingly so. And you see, therefore, that depending on the kind of question that you ask to your data, you get different p-values from these different tests. If you had asked what is the chance that 5 numbers sampled from 0 to 1 are all smaller than 0.25, this would be a different question that taking the product and saying how often does the product equal or is smaller than 4 10 to the minus 5, right? You would get a different answer. I hope this is clear now. Please interrupt me whenever you want and we can discuss. So going back to the analysis of CDF in run 1, they were getting, well, this is a set of maybe 10 or 11 p-values from 11 independent kinematic distributions of these 13 events, and they were all small. So this is a really interesting observation. It really does seem that these 13 events are nothing like what you would expect if they were sampled from standard model processes, because all of the p-values, all of these kinematical distributions look screwed up, and therefore the p-values are small. And you have also here in the middle, you see a graph of a control sample of data that have similar characteristics, but not the same set of events. And so this is a sort of a control sample, and you see that for the control sample, you do get a p-value distribution which is more or less flat. So they were making a test of a combination of these p-values, and they were getting a 6 sigma result. So the probability, the global probability that you would get a product of p-values so small as the one that you get from these was in fact amounting to 6 standard deviations. And you know that in physics, whatever is larger than 5 sigma it gives you a chance to claim that you have observed a new physics phenomenon. But when you are observing a new physics phenomenon above the standard model, and this is not explained by anything, so it is a really extraordinary claim that you are making. And so people didn't believe it, in fact. And so the real nature of these 13 events remained, in fact, mysterious until in run 2, the experiment had the chance to collect 10 times more data, and then 60, 70, 100 times more data. And these events didn't reappear. So they were related to the peculiarities of the detector, because the run 2 detector was different, was upgraded, and also probably due to having nitpicked a region of phase space where there was a funny concentration of events. So this was an a posteriori observation that the authors had led themselves into making, right? They constantly, they were scanning these events that were events where the top quark had been discovered earlier, and they were seeing that there was a concentration of phase space with some odd properties. So you should always be aware and careful of not doing this, right? You can certainly scan for anomalies, but then you have to be very careful at assessing the chance without defining a test statistic a posteriori that suits the anomalies that you see in your data. I wrote a whole book about this. It's called Anomaly, in fact. So again, you can check these discussions there. So this leads me.
So at the end, it seems it was a statistical fluctuation, no? Because they haven't this kind of events afterwards.
Yeah, no. So yeah, we can talk about the statistical fluctuation. Yes, it's a fluctuation indeed, but I would not even call it a fluctuation, because yes, if you take a uniform space, you can always find a fluctuation that gives you an overdensity in some part of the spectrum, right? But because of the stochasticity of the data that we collect, this is a normal fluctuation in a sense. It's not an abnormal. Yeah, you can call it very well a statistical fluctuation. But the point here is that it is found by a mechanism of a posterioriness, so scanning for overdensities in the data, right? Yeah, but it is correct to say that it is a statistical fluctuation. But if you reason only on this ground and you say it's a fluctuation, okay, but a 6 sigma fluctuation is really very, very rare. The point is that if you don't specify beforehand, you have to look. You have to look at the fact that you could have selected your region of interest in a gazillion different ways. So you have a very large trial factor. So the look elsewhere effect comes into play if you want. Okay. So if you allow yourself to select the region of interest as has been done in this particular case a posteriori, you can always find very, very, very small p-values for accumulations over densities of events. I hope this is, did I answer your question?
Yes, thank you. Okay.
So in fact, this matter had been discussed by this guy, Arthur Rosenfeld, who in 1968-69 published a paper because he was looking at the physics analysis that his colleagues were doing. And the people back then were looking for particle tracks in bubble chamber images of fixed target collisions. And so they were deriving 4 momenta of the observed charged particles, and with 4 momenta they could construct the mass of hypothetical particles that decayed into 2 or 3 charged particles. And what these people were doing was that they were looking for exotic hadrons. In 1964, the quark model had been conceived by Gell-Mann and Zweig. And this dictated that hadrons were only made by 3 quarks or quark-anti-quark pairs. So they were looking for new particles that could not fit in these SU3 octets, because you were classifying these particles as made of 3 quarks in various combinations. And so they were plotting histogram over histogram of mass distributions, and they were doing this day in and day out, and they were finding sometimes some piling up of data at a particular mass value. So they were claiming that they were seeing new resonances, particles that have a very well-defined mass, so that these Gaussian peaks stuck out on top of flattish backgrounds. And people were publishing these anomalies, and they were publishing many. And so this was a problem. So he said he was able to compute that the number of published claims of discovery of exotic particles, in fact, was more or less in line with the number that you would have expected of statistical fluctuations, given the number of places that these people were looking for fluctuations. Not only in many places in a mass histogram where you don't specify the mass a priori, but also in many, many different combinations of particles. So the issue was a large trial factor that was coming into play due to this massive use of combination. And so to quote this paper, this reasoning of multiplicity is extended to all combination of all outgoing particles and to all countries leads to an estimate of 35 million mass combination. How many histograms are plotted, the glance through blah. So the number we're looking is about 15,000 histograms. So how many fluctuations do we expect there? Many, right? About 10 to 100 deceptive upward fluctuation, probably of the level of 3 sigma or even larger. And the fact that you can combine many beams, because not only you are not specifying beforehand the mass of the particle you're looking for, you also are not specifying the width of the resonance. So you know that particles may have a narrow or a wide width depending on their lifetime. So this was a problem. And so he was advising to the theorists or phenomenologists, the moral is simply to wait for nearly 5 sigma effects, because this is really difficult to obtain even with a posteriori, even if you add a lot of trial factor, right? But okay, you want to publish, but if you publish, you have to be aware that anything that is smaller than 5 sigma or so, it's better be confirmed by another experiment before we are really sure and start drawing conclusion and cook up theories to embed this new particle. So yeah, I probably will skip this, but we are typically very bad at estimating significances, and we get drawn to narrow peaks more often than we are drawn to wider peaks. And that is because in case A, you see a peak sticks out much more prominently from a flattish background than in case C, where you have a wider peak. And all of these 3 peaks that you see in these pseudo experiment tests have a significance of 5 sigma if you actually compute it. And actually the fact that in case C, the peak is wider means that it has fewer chances of arising in the investigated mass distribution because it is wider. And so there are fewer places where such a deviation may appear than the narrow histogram on top. So there are issues with the fact that we are not very good with our eye to spot wider distributions than narrower ones. So we have selection biases of all kinds. It's not very important and not quantitative. So I don't want to discuss and spend much more time on this. But you understand the problem, right? So we tend to be more enamored with nice 3 beam bumps in a mass distribution or in a spectrum anyway. Narrow departures from the expected model, whatever the model is that we don't know before. The nasty part of all of this is that we not only forget to account for the possible places where a mass bump can arise, or the number of places that a significant fluctuation is arising in an otherwise smooth model, but we also always invariably forget to account for the fact that we have been inspecting many different histograms sometimes. Maybe we changed the selection that we subjected our data to. And every time that you change your selection, you get a new data set, well, maybe, of course, correlated with the others. But then if you look for features that are not captured by the model that you expect, maybe your Monte Carlo simulation or standard model processes or whatever you want, you are going to get interesting statistical fluctuations that you concentrate on, and then you make things even harder because you will want to make the case stronger for having observed something. So be very careful of modifying your selection a posteriori, okay? So the end result is that before internal review of analysis, typically a 4 sigma effect in a typical LHC experiment happen very often, much more often than what the p-value is for 4 sigmas. And in fact, Sometimes we even publish them without realizing that, that in fact, there's a posterioriness built in the process. Okay. This is just an example, again, drawn by the past history. Again, it's also discussed in the book. Now, we will now do a tutorial where we estimate tail probabilities with and without significances for Poisson data, so a counting experiment. But let me make a couple of points here. Both in astroparticle and in particle physics and in neutrino physics, we do counting experiments. We count events from a common Poisson, common rate Poisson process. And then we look for something new, some additional process on top of backgrounds. And the significance that we draw is measured by converting that mathematical map that takes a p-value and makes a number of sigma out of that, as we discussed in the other lecture. So typically we will have B events from background, and we will test for a contributing signal on top of it. So if we want to write the probability for observing n events when the background is, when the mean rate is B plus S, this is of course a Poisson of B plus S given we observe n given B plus S as mean. And so when we observe an OBS event, we can assign the tail probability as the probability of observing a small n larger or equal to the observed number that we got. And this is easily calculated as 1 minus the probability, the sum from 0 to n OBS minus 1 of the Poisson term. Why do we do this trick of 1 minus sum from 0 to n OBS minus 1? Of course, because it is much more practical to compute a sum from 0 to n OBS minus 1 than computing an integral from n OBS to infinity. Okay, you would have to add up an infinite sum of almost null terms. Okay, but this a point to make is not the probability that the null hypothesis, the hypothesis that n is drawn from the background alone that you have put in this Poisson term without the signal, you see, b to the n e to the minus b divided by n factorial. This is not the probability of the background model alone being true. This is not what a frequentist does. The frequentist never talks about the probability of a hypothesis, okay? This is the probability that if the background only hypothesis is true, we observe at least an OBS events. A numerical example, take b equal 1.1, 10 observed events, then the tail probability is 2.6 and e to the minus 7, which is exactly 5 sigma. A similar situation for getting 5 sigma is if your background is expected to be 0.05 and you observe 4 events. 4 events are enough for a 5 sigma claim if the background is almost null, okay? If the background is null, observing 1 event is infinite number of sigmas because no fluctuation of the background will produce 1 event, all right? But also note that if you use a small number of events to measure a cross-section for a known process, you will have larger error bars if the number of events is small, of course, because for a Poisson process, the variance is equal to the mean. So small mean means also small variance, but the ratio between mean and variance becomes, sorry, the root mean square is the square root of the variance. So you get this fact that the percentage uncertainty becomes smaller as the number increases. For a very small number of events, the percentage uncertainty is large. For instance, if the background is expected to be 0 and you observe 5 events, well, then you can attribute all of the 5 events to the signal process. And if you compute the likelihood ratio intervals for these situations, we have done it 2 days ago, if you will remember, give you an interval from 3 to 7.5. Okay, now one point to make is you have measured S equal 5 minus 1.92 plus 2.558. Now, if you look at this number and in isolation, say that your friend says, I measured the process to be 5 plus or minus 2, okay, or 2.5 or whatever. And you say, oh, okay, that is different from 0, but it is not terribly so. It is compatible with 0 at the 2.5 sigma level, because 5 is 2.5 sigma away from 0 if you take 1.92 to be the sigma, right? The negative fluctuation. But this is a false observation, because in fact the significance of observing 5 events is infinite. So please don't confuse yourself into counting how far away you are from 0 in number of observed standard deviations. This is not something that you can do in this case. Okay, I hope this is clear. Then finally, we always have to cope with systematic uncertainty in our measurements. And in fact, Rosenfeld's criterion for a 5 sigma, maybe I shouldn't go forward with the slides until I tell you this, so that you can concentrate on what I'm telling you. Rosenfeld was claiming that we should wait for 5 sigma effects to publish a discovery because of trials factors. But indeed, in the practice of experimental physics, we have started to use the 5 sigma criterion more to protect ourselves from unknown systematic uncertainties, because the look elsewhere effect we can sort of correct for. Okay, we have actually started to publish results of physics analysis where we say, this is the significance if I only consider this mass range where I look for the particle, and if I consider a wider mass range, the significance goes down. So I publish more numbers for the significance. I am giving a more detailed discussion of this, and this is always good to do. And so we have local and global significances, so we can sort of account for the trials factor. But what we cannot do is account for unknown systematic uncertainties that are widening our confidence intervals at our without us knowing it. So that is part of the reason why the 5 sigma criterion has kept has lingered around. And in fact, particle searches in the 70s and in the 80s didn't use the 5 sigma criterion much, but starting with the top quark discovery, it was followed very diligently, okay, and people still use it, and it's consolidated, although it is entirely ad hoc, because why 5 sigma, why not 6, why not 4, all right? It's it's a choice of a type 1 error rate, and it's arbitrary, but you know, statistics gives you different answers if you ask different questions. That is, we have to live with it, okay? So it's a convention that we can publish an observation only above 5 sigma. But the reason why we wait is that sometimes we don't know. These particle processes are complicated, and sometimes we have systematic uncertainties we don't know about. What we can do typically when we know that we may have a systematic effect, a mismodeling or something like that, is to size up the typical variation of an observable due to imprecise modeling. So for instance, the background may be uncertain to some level. So we assess the variation of the background at 1 sigma. We say, if I change the model this way, the background will change to this number. If I change the model on the other side, the background will grow. And so I have a plus or minus 1 sigma estimate. And what I do then, I say, okay, this will be a Gaussian distribution. So I model my uncertainty, my systematic uncertainty as a Gaussian distribution. I smear the background estimate with that. And then I can do the inference and say that I have accounted for that systematic. But we never know what the density function that we are sampling this systematic effect from is really. So assuming that is a Gaussian, it's just throwing our hands up because we don't know what to do. But it is liable to be wrong, especially in the tails, because you know the Gaussian goes down to very, very quickly in the tails. But if you have a different probability density function for a nuisance parameter, a systematic uncertainty, you may pay a very large price when you estimate your significance, because this systematic uncertainty actually might be causing you to neglect its effect on the tails. So the potential harm of large non-Gaussian tails of systematic effects is one reason for sticking to 5 sigma significance. And in fact, 5 sigma doesn't even cover you from the pitfalls that you may have by considering Gaussian distributions of the systematics. Let's make a quick example. Okay, imagine that the 5 sigma effect is in fact an effect dominated by systematics. What I mean to say is that the uncertainty, the 1 sigma uncertainty in your result is most of it is due to a systematic uncertainty, not a statistical one. You have a very large statistical effect, but then you have a large systematic, which is driving how far you are from the null hypothesis. So you get 5 sigma because of this systematic. And imagine that you have underestimated your systematic uncertainty by a factor of 2. That is not so uncommon. So the 5 sigma effect is actually a 2.5 sigma one, because the RMS of this systematic effect is twice as big. Now, you could come and say, I could be your advisor, and you come and tell me, oh, okay, I have a 5 sigma effect here. And then I point out that you have underestimated your systematics by a factor of 2, and you say, okay, I made a mistake by a factor of 2. Do you want to kill me for that? Yes, I do want to kill you, because in terms of a p-value, you have not underestimated the p-value by a factor of 2. You have underestimated the p-value by a factor of 20,000. Okay, so you made a big mistake. What I'm trying to say is that if you reason in significance units, you have to realize that the tails of a Gaussian go down very quickly, and what you should reason in terms of is p-values. Okay, so be very careful. In fact, there's a study of residual. Yes.
Systematic effects. One problem I need to identify is the estimate of this systematic estimation for these systematic effects. But sometimes, for example, it's difficult. For example, the case you mentioned about the omega experiment, well, of course, the result was completely dominated by a systematic effect, which was that the Kyball wasn't well connected. So, is it really easy to give a right estimate of these systematics?
No, it is never easy. In fact, it's very hard, and it's in fact what distinguishes a good physicist from an average one, the capability of cooking up tests that pinpoint these nuisance parameters. It is always very hard because, you know, there may be mismodeling systematics. So I don't know, you have a certain Monte Carlo, and the Monte Carlo assumes a parameter of nature in deriving your distribution, your model. And then you say, okay, I can always go back and change that parameter in the Monte Carlo and see what the variation is. And I can do this actually for various numbers. And so I can cook up a very good study of that systematic effect. But this is only the easy part. The hard part is that sometimes really we don't know what is the source of our systematic uncertainty. And those are the cases where we cannot do much. So it is a little bit of a case-by-case situation, how much of studies, how many studies, how deep studies you can make about an experimental situation. I don't know if I answered your question because there was some noise. I'm not sure I got it completely. Okay. So to show you that residual systematic uncertainties are not Gaussian typically, There was Mats Ross, a guy that with some others considered the residuals in particle physics measurements or particle physics properties, hadron mean life and mass measurements, done by particle physicists using particle physics data. So here we have an example of something very well controlled. So the kind of inference that particle physicists do, and they were able to extract the residuals, which is this curve here on the top right, in units of sigma of the result from the true value. So you have a result, you measure something to be 100 plus or minus 10, and you don't know what the true value is. But then much later, somebody determines that true value much more precisely. We know that it is 102 plus or minus 0.1. So you can actually see how far your measurement actually was in units of your claimed standard deviation. So 100 plus or minus 10 is actually 0.2 sigma away from 102. So there you get a 0.2 entry in this histogram. So this is a pooled distribution. And they were able to study this with hundreds of different physics measurements. And so they derived the actual distribution of the pools of particle physics measurements. And you can see that it is not a Gaussian by any means. In fact, it is a student 10 distribution, which is a sort of Gaussian-ish distribution, but it has longer tails than the Gaussian. Does it make a difference? Well, it does, because if you are in the 1 sigma regime, they are not very different, these two curves, and you see it on the bottom left. But if you look at the ratio between the sigma, the student 10 distribution and the Gaussian, by the time you hit 5 sigma significance, the tails of the student are 1,000 times higher. So here you see particle physics measurements done by particle physicists that misunderstood the tails of their results by a large amount. This is a problem because this may cause you to publish the discovery of an effect, because it makes the 5 sigma effect 1,000 times more likely than it actually is, okay? And actually there was a similar study made much more recently, and this guy looked at a lot of different databases and was able to derive these pool distributions in these 4 cases you see. And you expect a normal distribution. It's the dashed lines here on the right. And you see how different the tails in number of standard deviations are from what you expect. So this again points you to the fact that typically we underestimate the tail of our measurements. Okay. So I think we can leave this Gaussian Jeffreys-Lindley paradox and just conclude. Okay, statistics is not trivial, and making the right choices for what method to use is very important. I showed you how having better estimators makes for better estimates. And of course, I also showed you a little bit how you should avoid to make probability inversion statements if you decide to be a classical statistician, or wrong apologetic sentences, improper uses of the likelihood function, and so on. So, okay, we took enough time to finish these slides, and now I want to go to the tutorial, okay? If you have a laptop and were able to actually install the root program, you will be able to actually download from these areas these pieces of code, and you can try and run them by yourself if you want. But this is not necessary because you can do this offline. Right now, we will just describe these programs that are doing very simple things, and we can check what they can allow us to investigate. You should also know that the code was written using the 5.3 version of root, and now root has a version 6. So if you try to compile this code by using capital L, the name of the file plus, this compiles the macro such that it runs faster. It may give you some strange errors and not run. Then try to run it without compiling it, and the compiler will then, the interpreter will give you more insight. And typically root 5 to root 6. Root 6 is a little bit less forgiving for variables that are not defined or things like that. It typically is easy to debug. I'm sorry for this misalignment, but I don't think it will stop us from doing what we want now. So I promised we will look into this tail probability calculation, and it is trivial, but then we will be able to do it by inserting a nuisance parameter, and things become a little bit more interesting. So we want to write a root macro that inputs expected background counts right now with no error and observed events n, and computes the probability of observing at least n events. So it's a positive tail probability that we want, and the corresponding number of sigmas for a one-tailed Gaussian test. Okay, so this mathematical map we were talking about all along. So the p-value calculation should be easy for you to code in C or in any other programming language you're going to use, because you just have to sum from 0 to n minus 1, and then you take 1 minus sum. That is the integral from n to infinity. And the probability density function is discrete, so it's easy to do. And deriving the number of sigmas that the p-value corresponds to just requires you to make a call to the Earth inverse function. And this is available in the tmaths package, which is linked when you include it in your header file in your program. Or but in the code that you see in that area I pointed to before, it's explicitly listed at the bottom of the macro so that you can look at it. And for the sake of it, since root gives you the chance of plotting histograms, you can actually plot the probability distribution function of observing n events when the mean is mu, so b, n events when the mean is b, sorry. And then you can do show this in linear and semi-log distribution, and highlight the portion of the graph for the data that you observed, so that you actually can look at something nice. All right. So we will do that. Actually, it's already done, as we said. So we will look at the code rather than coding it ourselves. Of course, then you can change things and see what happens. By the way, the Earth function is this one, is the integral of a Gaussian. And it's a useful thing to know in statistics, and it allows you to derive these p-values, integrals of Gaussians very quickly. Now, let us first look at the implementation of this code. So you will have the core of the program will be a call to a routine called Poisson probe fix, because we fix the background to be equal to b, and we have n events, and these are pass parameters. Then we define a number that is just useful for the range of these histograms. You see th1d star is defining a histogram which has max n beans that run from 0 to max n, okay? And we have two such histograms because one of them we want to draw it in blue on top of the other, so that we see the events greater, the part of the Poisson that has at least n events observed. And we can define this max n to be 1.5 times the number observed, or 2 times the number observed if the number is small, so that we can have nice graphs. But the core of the calculation is here. We have a sum that we initialize at 0. And then we need a factorial function, because the Poisson has a factorial, right? So you loop from 0 to the maximum number in the histogram, because you want to fill this distribution in the histogram. And then you multiply this factorial by I, going from 0 to a certain I. And as you go along, you compute the Poisson term, which is exponential of minus b times power of b to the I divided by the factorial. So these are the factorial terms for I equals 0, 1, 2, 3, 4, and so on. And so you sum these numbers if they are less than n, and then you fill these histograms, Poisson and Poisson GT, with set bin content. And at the end, you compute the p-value as 1 minus the sum, and the z-value as this Estimat F inverse function. And then you dump the results. So let's play with this, okay? We have a toy, you can download the function, and we can play with it. Why doing it is because it is good actually to become able to guess from the numbers given what the p-values or the signal are. So this is the macro, and you see that I have a bunch of headers that allow me to use one-dimensional histograms and canvases. And then I have a Estimat include, and I have a random number generator if I ever need it. But okay, I don't need it in this particular macro. The macro will not run for too large number of events, so I have some couts here. But with particular combinations of B and N, it will still crash because the factorial becomes too large for these numbers, for this particular kind of precision. So, all right, let me run it for you, and let's answer together these questions I have. So before we run it, you have 5 events of background and you observe 20 events. You are very lucky because you say, okay, this is very significant. How significant is it in terms of sigma? So if B was 5 plus or minus square root of 5, if this was a Gaussian measurement, 20 would be 15 more than 5, and the 15 divided by square root of 5, well, square root of 5 is 2.2, so 15 divided by 2.2 is actually, what, 7 sigma or so. So is it 7 sigma? No, it's a little bit less because the Poisson has longer tails than the Gaussian. Let's try it, okay? So I do dot L, Poisson, prob, fix, dot C plus, and it will compile. Can you see my root screen?
Yes, the letters are small, but...
Yeah, unfortunately, I cannot make them bigger, but I can read things off for you. So, and now I can run Poisson, prob, fix. I just call the function, and with the tab, I can remind myself what I need to put. So I will put 5 for the background and 20 for the signal. And this will give me this nice graph, which will highlight the fact that this tail is very small. And in fact, if I read off the result, the probability is 3 × 10⁻⁷. That corresponds to a little bit less than 5 sigma. Okay, so not 7 sigma, but 5. That's because the Poisson is not the Gaussian, okay? Exercise 2, the background is now equal to 10 with no uncertainty. What is the signal if the number of sigmas is 3? This is an inverse question, okay? So you cannot really use this program, but you can try it in many instances. So I will put 10 here, and I will try to find the S such that I get returned 3 sigma. So if I try with 20 total events and 10 background events, I get to 2.7 sigma. So I need to increase the number from 20 total to maybe 22 total. 22 total is already 3.2 sigma, so maybe 21. Well, 21 is more or less 3 sigma, okay? What if we want 5 sigma? How many events do we have observed? Do we need to observe if the background is 10? Well, we probably have to go up to 30 or something, no? So this is in fact 30. We get very close, 5 sigma. So you see, I was sort of driven by my prior experience with p-values and sigmas, so that I was able to guesstimate that with 10 background events of background very well known, you need 30 events of total observation in order to get to 5 sigma for a counting experiment. Okay. All right. So let's not waste our time with this, but you can play more. Sorry. Yeah.
Click with the right button on the bar. Then you go to properties, and then you can change the size of the letter. Yes, over the bar of the window. The upper part.
Sorry, here you mean?
Yes, here. Then you go to properties at the very end.
Ah, sorry.
Yes, it is at the end properties.
Yeah, but it doesn't work, you know.
But I think you need to again, put the mouse clicks on the upper part, then right click, and then you go down properties. This proprietà.
I think
yes, and then you go second tab probably. Yes, you can change now the size of the.
Okay, okay, very good. Yeah. Do you see better now?
Yeah, it could be even larger.
Even larger, okay. Okay.
Yes, very good. Thank you.
All right. Okay, so let's now move on to another thing, because typically you will not know the background with infinite precision. You will know it with a certain uncertainty. Okay, so let's now try to model this into this functionality into our macro. So what it means if your background is not known precisely, but with a certain uncertainty, is that you will have to do toys whereby you throw a number from, say, a Gaussian distribution centered at your nominal background with a width of the specified uncertainty on the background. And you will use that as your background in determining the tail probability. And then you will go back and throw another B number from the distribution, and you determine a new p-value, and you continue to do this for a large number of trials, so that you sample the distribution function that gives you the background, and you can get a set of p-values for a given observed number n. And what do you do with this set? Well, you can take the median distribution or of this distribution, or the mean, and that is the mean p-value that you expect from observing n or more events when the background is b plus or minus sigma b. So this is implementing the uncertainty in your background expectation. So what we need to implement in the macro is to throw a random number b equals g of b prime sigma b, where you actually have provided b prime and sigma b in the body of your call to the macro. And then you take the average. Why the average? You could take the median, but okay, this again has to do with the fact that you can ask these different questions and they will be, the answer you get is different. But okay, one subtlety here is that you will have to enforce that b is non-negative, because the Gaussian has tail to minus infinity, and sometimes the sampling of a Gaussian will return a negative b value. What do you do with it? And do you resample from the starting distribution, or do you set b to 0? Depending what you do, you will get a different p-value distribution. So you see that the devil is in the details. And when you report the physics measurements, you have to be very careful in reporting exactly what you did, because the answer you get is different, and this bears on the reproducibility of your results. You want your results to be reproducible such that it's not criticizable. So you better be careful to say, I trimmed the negative B values, or I re-sampled them, okay? In this case, you see that we are trimming them. We are not cutting them away. So you see that this distribution of possible backgrounds is of course, it doesn't extend to negative values here on the top left of your histogram. What you see is that we have put all of these events that would fall in the negative part of the distribution at 0. Okay, but that is a different result than if we just ignore them and plot only the positive part of the distribution. So the answer will be different. Okay, this is a possible way to implement it. And you see that we get to pass parameters B and SB, the uncertainty on B. Here we want to add, apart from 2 histograms that one give you the p-value distribution, because instead of having one single p-value, we will have a distribution now when you want to plot it. But the core of it is that you sample a number of times. You run this iterator from 0 to n iterations, and I've set 10,000 here, but you can change it if you want. But 10,000 is enough to have a smooth distribution of p-values out of it. And you sample this B to be a random Gaussian number from a mean B and a sigma SB. And then you fill the background because you want to see it. And then you do your calculation of the p-value as you did before. So let's see how this works. So I need to take a new root window here. Sorry, I'm messing up. Okay, so let's load the Poisson probe FLAC, which you can also find in, and I can run this with some choice. So let's try the first exercise. We have 0.1 events of background plus or minus 0.1. And we observe 3 events. What is the significance in sigmas? Well, 3, as we said, is very different from 0.1. In fact, it's very hard from 0.1 to go all the way to 3. So let's see, this should be a large number, right? And here we get it. We get that the probability is 3.25 sigma. So you see, we are sort of puzzled here. Why such a small probability? 3 in units of 0.1 is very far from 0.1. If 0.1 was a Gaussian center there with a width of 0.1, you would be at 29 sigma away from 0.1 when you measure 3. But you see the difference. The Gaussian goes down much faster than does the Poisson. And since you are sampling a number of mean 0.1 with a width of 0.1, sometimes the background fluctuates to 0.4 or 0.5. And when it does, the probability of obtaining 3 is not any longer so small. And when you sum many possible cases, this count when you are looking for very small probabilities, and you get a number of sigma, which is not so small. Okay. Second example, B is equal to 2 plus or minus 1, and signal is 10. What is the significance? Let's try it. 2 plus or minus 1, so 2, 1, and 10. This time we have 3.1 sigma, okay? And the code also tells you, please beware, we trimmed out 2.25% of the experiments because, you know, in this case, this background of 2 plus or minus 1 means that sometimes it was getting negative values of B, and we cannot live with that because the exponential, so the Poisson doesn't exist. So we have to do something about that. But all right, this is just a warning that we get. So you can play with this also, and you can ask yourself, I have a background of 0.5 events and with a certain uncertainty, and I see 5 events. How much do I have to beat down my systematics on B such that the significance of this observation is 3 sigma? Well, this means inverting what the code does, but we can try. So the numbers here are 0.5, X, and 5. So let's try a few numbers and see when we get to 3 sigma, okay? So we can do so 0.5 something and 5. 3 sigma. Does anybody want to guess what I should put here to get 3 sigma? Should I put that the background has an uncertainty of 1, or should I put a smaller number, for instance? I know that this doesn't work very well online, so rather than asking you for questions, unfortunately, I'm not there with you. I would like to be there with you, but well, it was not possible. So let's try 1 as an uncertainty. And there we get 2.25 sigma. So the uncertainty is too large for 5 to be 3 sigma away from 0.5. So let's try 0.5. We get to 2.84 sigma. So again, it's too large. 0.3 maybe. 0.3 is above 3 sigma. So if you have a background of 0.5 plus or minus 0.3, observing 5 or more events for a counting experiment is 3.1 sigma. Okay. There's not much more to know about this, but it's I think nice for you to play with this code, to modify it such that it handles differently negative values, or even try different nuisance distributions. In fact, we have put a Gaussian distribution for a background uncertainty, but that is silly because the background is typically known to within a certain factor. So maybe you know that the background is 5, and it's not 5 plus or minus 2, it's 5 plus or minus 20% or 40%. So how do you model a percent uncertainty? You model it with a log normal distribution. So if you change the code, and this is a good exercise for you for the break today or this evening, if you code a log normal sampling of the background instead of a Gaussian, you will not have any longer the problem of the background going negative as when you're modeling with a Gaussian, which is silly, but it is easy. And so you will be able to see how much of a difference it makes with respect to the Gaussian nuisance. Okay, so this is a nice extension of the macro that you have. Okay, let's move on to testing the Fisher F-test. We discussed the Fisher F-test already, and you have seen these slides already. So now you know what awaits you. We can play with the macro, and the macro is still in that area that I pointed at before. So the macro allows you to state a type 1 error rate because it's a test. It's a goodness of fit test. It's actually a hypothesis test. You expect that if you model data from a uniform distribution and you try to fit it with a linear or with a quadratic, sometimes the data will fluctuate and make the F-test prefer the more complex model. So we could, in fact, measure whether the number of times that the Fisher F-test fails to give you the right model is, we could do it by resampling this. It's a bit tedious to implement this in the code. It's nothing difficult anyways, you can do it. But let's instead run this macro manually. So let's go back here and I will load the ftest commented.c, I think. This is how it's called. And in this macro, I need to pass the number of beans of the histogram that I want to study. the number of data that I'm going to fill in this histogram, and a type 1 error rate. And then I have an option. So rather than pondering what this means, let's look at the code. And the code is here. Here I actually know how to change the font. Okay, let's do it like this. So this is the ftest commented macro, okay? Bunch of includes, and then the function has these pass parameters, and okay, you have to fill a few histograms such that you can show the data that you have generated. It's a one-shot data set, so you can look at it. And then you want to also fill histograms with the F distributions for the various hypotheses. So option equals 0 is a pass parameter which will generate a constant distribution. And then you can fit it with a constant, with a linear, or with a quadratic function, or with a cubic, and see what the ftest discriminating the constant to the line, or the line from the quadratic, and the quadratic with the cubic comes out. Or you can generate a linear distribution and do the same thing, or generate a quadratic if option is equal to 2. Or even you can do something different. You generate a falling exponential and you try to fit it with polynomials. So none of these models is good. So the ftest will give you some answer, and then you will choose a model, but the model will not be correct anyways. And this can happen, right? But the polynomial approximates any function if you have a large number of parameters. So for some data, an exponential is well approximated by a linear, or for more data, it is better approximated by a quadratic. So you can play with it. So I will not go into details of how this code is actually written, but the core of the code is the calculation of this ftest, which is actually provided in Tmath. Okay, so there's not much. It's only to compute this distance of chi-squareds that you sum here, and then you use them for the comparison. So let's try it. Let's try to say that we have 10 beans and 1,000 events. And with a type 1 error rate of 0.1, we want to see whether data that is generated with a constant distribution, what does the test tell us? So here you see how the fit to a constant, to a linear, to a quadratic, and to a cubic is for this set of data points. And you see the three tests in these three histograms, these three panels. And so here you are comparing constant to line, line to quadratic, and quadratic to cubic. And the output here that the test gives you very large F values, and it says no need for anything more than a constant fit. So the ftest has actually allowed us to do model selection correctly. We generated data from a constant, and we got that the constant fit is the right thing. And now let's try maybe a different number of beans, or even a smaller number of beans, and generate a linear function and the test with type 1 error rate of 0.1, test a constant, line, quadratic, and cubic in terms. And here you see that, of course, this linear data, in this case, have a large slope. You can change it in the code, but in this case, it is very easy for the test to determine that a constant fit is bad. But a linear fit is, of course, good. And a quadratic fit doesn't find any reason for a slope. No, so neither does a cubic. So already by looking at these graphs, we sort of know, we would be surprised if the test hadn't identified that a linear fit is sufficient, right? And in fact, a linear fit is sufficient to describe this data. And these are the numbers, the p-values of the tests. Of course, you see that the constant to line f-test is very small. So it is excluded at the type 1 error rate, which is larger than 10 to the minus 4. Now let's try, maybe things get a little bit more interesting if we decrease the number of data, because then the power of the data is smaller, and we will try to generate a quadratic data set and see what the Fisher test does. And you see that again, this quadratic data set is well fit by a quadratic, and it is reasonably fit also by a linear function. So in fact, it says a linear fit is sufficient to describe this data, because the f-test is already equal to 1. So it's so what does this tell you is that when you have little data, your model selection is not very powerful. It doesn't allow you to select a model very well, because you cannot very well distinguish a quadratic from a linear distribution when you have too few events. Okay, so you can play with this code. One interesting thing is to try the exponential distribution, and maybe five beans, 1,000 points, and see what happens. And you will find that, okay, you have four different possible models to fit this exponential data. And of course, the constant won't do it. But in this case, neither does the linear, because the data is actually precise. But the quadratic will do a decent job typically. And you will not need the parameters, the added parameter of a cubic fit. And this is typically happening also for larger number of events, if I remember. You see, quadratic tends to do a decent job, although not a perfect one, okay? So you can learn stuff by playing with the f-test, I think. Are there questions, or shall we move on?
Are there any questions? No. So we can.
Okay. Okay. So let's go on. You can extend the, well, I already extended the code to exponentials, but you will, you can of course create a set of models that are exponentials of polynomials. And then you have an additive number of parameters. You can have 0 parameters, 1, 2, 3, and so an exponential of a polynomial series, alpha plus alpha 0 plus alpha 1 times x plus alpha 2 times x squared plus alpha 3 times x cubed, and so on. As you increase the number of parameters, you get more flexibility for these exponential models. And you can try with exponential models to see if you can fit the data that are drawn from more complex functions. And you can have fun and add functionality to this macro. The one thing that is a little bit complicated is that whenever you insert a new model, you have to generate the data according to the true model. And to generate the data, typically you will not have, in your random functions, you will not have the possibility to generate data according to any model. It allows you to draw data from a Gaussian or from a Poisson, but not from anything. So you will generate uniform data, and then you will calculate the integral of the model, and then do the inverse of the cumulative distribution function to get a number distributed from as any function that you want. So this is the Monte Carlo method, basically. You draw a number from a uniform distribution, you look up what is the value of the cumulative distribution that corresponds to that, and that will give you a distribution of numbers that distribute as the inverse of the cumulative for the model that you've chosen. So if this is not clear, look at this code or look up in Wikipedia what is a cumulative distribution function, and it will become clear. So we can move to confidence intervals, in fact, because we were discussing the Wilson score and the Wald interval for the binomial ratio. This is one of those cases with discrete distributions where having perfect coverage is impossible, because as you will remember that you construct the confidence belt by integrating the distribution function of some measured data x given parameter theta, such that you engulf 68.3% of the integral of the distribution or whatever you want given your alpha level. And this is impossible to do precisely if the distribution is discrete. So the binomial is one such case when you have a discrete distribution, when you have you are, for instance, counting how many heads you have in some flips of a coin. So successes versus trials, S versus T. Okay, this is a binomial process, and the correct coverage was derived first by Klopper and Pearsons, who inverted the binomial test using Neymann's prescription. And these actually overcover a lot because they, by definition, never cover less than 68.3% of the time. This made a number of alternatives flourish. So Wald, who is famous for having inferred something about planes that were hit by bullets during World War II. And okay, that's another story. You can look up Wald. He was an interesting character. But this is the formula for the estimation of the variance of a given binomial trial done t times when the binomial ratio is rho. As we said, this is an estimate of the variance of the root mean square. And if you do estimated rho plus or minus 1 sigma, you have intervals that cover very badly when rho is large or is small. So in fact, we can try the Wilson score interval that does a better job. And it's just, it's defined in this way. I won't go in the formula, but we want to write a program that compares the Wilson score intervals coverage to the Wald coverage. So first of all, let's try a program called Wilson.c, which computes a single time the two intervals for given a type 1 error rate, so 68.3%, that means alpha is 31.8%, or whatever else you want, for different values of successes and trials. So let's look at the code first. The code, well, I don't have it. I need to open it. Wilson.c. I have a lot of stuff here. So Wilson.c. Okay, this is the code. And you see that it is very, very quick to compute. You have the formulas I have in the slide are reported here. And so you pass the number of successes and trials and the type 1 error rate, and it computes the intervals for that. So let's try it, okay? I compile the code. It was already there. So Wilson. So let's try 2 successes out of 20 trials at a type 1 error rate of 0.1. What does happen here is that, of course, the maximum likelihood estimate is 0.1, 2 out of 20, right? The Wald interval will give you an interval in 0 to 0.21. And the Wilson score interval will actually give you an interval which extends a little bit above 0, but to 0.26. So it's considerably wider. Okay. Let's try what happens for 9 and 20. So a number close to 5.5. Here you see that the difference between the two intervals is not very large, because as I said, the Wald interval is actually not so bad in the center, but it's very bad for very small and very large values. So let's try the Wilson score interval program with 19 trials, successes out of 20 trials. You see that there is a very large difference. And if I increase this to be, let's say, 199 to 200, the world interval is 0.987 to 1, and the Wilson score is 0.977. So, okay, there is a difference in these coverages, but it doesn't ring a bell. It doesn't seem like we need to use the Wilson score interval. It looks like there are two different estimates for intervals. So let's try to do this and estimate the coverage. So how do we compute the coverage? We have to take a value of rho and generate many times a data set with a different number of successes sampled with a given value of rho from n trials. So this time we will not give the number of successes. It will be a variable in the toy generation. We only give the number of trials that we make. That will be actually the variable, if you want, the ancillary variable that gives us a measure of the precision of our estimate of rho. And so we can test the coverage of the two intervals in different setups, okay? Good, so here is the implementation I put together of Wilson coverage.c. Let me again increase the font. Okay, so here we do the same thing that we did before, but we also fill a couple of histograms with the coverage as a function of rho from 0 to 1. So 100 beans. So we loop over 100 possible values of rho. I true is equal to 0 to 100, and rho true is this value. And then we do repetitions of toys where we generate data according to a binomial. So the signal, the number of successes is actually sampled from a binomial. And we do our studies of the intervals, and then we check whether the true value is within the measured intervals for Wald and for Wilson, and we plot it, okay? So let's see what happens. So Wilson coverage. Now let's try 100 trials. So 100 trials. Let's do 1,000 repetitions so that our histograms will look nice for a type 1 error rate of 0.1. Here you see what the coverage is. At the alpha level of 0.1, you expect 90% coverage, and that is more or less what happens with Wilson and Wald. But you see that the Wald interval fails miserably when rho is very small or very large. And this is due to the fact that, in fact, the Wald interval collapses to 0 widths when actually the number of successes is 0 or is equal to the number of trials. While the Wilson coverage does a good job in all of the spectrum. You can try for a smaller number of trials, and you will see that the effect becomes more dramatic. Here I am only having 10 trials, and the number of successes varies, and this is the factor rho. And you see that the Wilson score intervals does a good job at covering at the stated confidence interval, while the Wald interval does a terrible job on large or small number of successes. That is to say, sorry, small or large numbers of the binomial ratio rho. Okay, so you can change the type 1 error rate and see what happens. So this is, for instance, for 1 sigma. It's centered around 0.68, but again, there is significant undercoverage on the tails. So you see, you can draw intervals with different recipes, and they will have different coverage properties. Ultimately, it is better to have coverage because the intervals that you quote are more in line with what you tell the consumer about your uncertainties. But if you specify what you are doing, well, it may be criticizable, but at least it is clear what you have been doing. Okay, so I think this is all I wanted to show you. of course, I encourage you to do these exercises. One of them is to implement more functionality in the F-test. I suggested you to implement a log normal nuisance in the tail probability. These root macros, or if you code them with Python or with whatever other program, they will still be with you for a long time, because if you continue to do research during your PhD and after, you will find that it is very useful to have these macros handy. And of course, you can build more functionality and more complex calculations on top of them, or use these templates to do toys for other problems. I think in my lectures, I have given you several examples of how useful it is to actually do frequentist calculations with random generation of toys. It is really enlightening, I think, to do so, because generation of toys allows you really to understand what is going on and why you get a certain result from a test. And what happens if you change your prior? What happens if you change your nuisance parameter? All of these things, I think, getting familiar with these potential variations will give you, will sort of expand your horizons in the sense that you will be able to by analogy to examples you worked out, you will be able to be more likely to guess what happens in an unknown new situation of data analysis. So I encourage you really to do so. You can build your own arsenal of weapons. As I shown you, I have a gazillion macros here in this area, because I over time I have tested many things with toys or programs that do this kind of calculations. Okay, so if you have questions, I'm here, and if not, I will be happy to answer questions offline when you try these programs yourselves.
Okay, so thank you very much. I think it has been very illuminating to see all these codes running live. So thank you very much, Tommaso.
You're welcome.
So do you have any questions?
Okay, you can always ask questions offline. So
curiosity, I imagine perhaps that you are familiar with the data result for research of Karl Matter, where they are seeing an annual modulation since a lot of time ago. And well, you see directly by eye, they plots. It is really impressive to see this annual modulation. Now, I'm not familiar really with the exact statistical computation they do to affirm that they are seeing this annual modulation. Do you know about this? Do you know what's your opinion about this case?
So you're talking about Dama Libra?
Yes, Dama Libra, yes.
So yeah, the Dama collaboration has been reporting an annual modulation of the number of counts in their cesium iodide detectors for a long time. And this it's actually a funny story, because they started showing that it was a 4 or 5 sigma effect, and then they added more data, and this became even more precise, and they have continued to do so for a long time, when in fact at some point they could have even stopped, because when your statistical uncertainty on the parameter you're estimating is becoming very small, and the question is only about the systematic uncertainties, it makes really no sense to continue running your apparatus for more precision in statistical uncertainty. You want to estimate, to spend all your time in looking for systematic effects. So there have been a number of possible criticisms, things that might happen in to cesium iodide, seasonal variations of the response. And it has not helped much the fact that the collaboration has been a little bit opaque in showing the original distribution of event counts from which they were deriving this excess, of which they were showing this nice modulation. So it has always been a little bit difficult to evaluate really how seriously to take this result. Of course, from a phenomenological standpoint, it has always been also very complicated because other experiments were not testing exactly the same thing, but they were not in compatibility with gamma at all. And so now there are other experiments that are trying to do exactly the same measurement. But from a statistical point of view, I think I have to criticize the fact that they didn't provide the original distributions, but only the vetted distribution of background subtracted data. And this has caused problems. You should always put as much information as possible available to your reviewers and the consumers such that they can make up their mind more clearly. But another observation is that, I already made it. I think the focus, when the focus becomes the systematic uncertainties, really, you need to cook up good alternative tests. It doesn't matter that you continue to see these oscillations as you continue to take data, because everybody is convinced that this is a systematic effect. What is called, it's not a statistical fluctuation. You see a systematic oscillation in the counts at 6 months half period. So this means that it's a systematic effect. It doesn't mean that the systematic is really an error. It is maybe a systematic effect caused by a contribution from dark matter interaction in your detector. It still is a systematic effect. And you can try tests to see how to pinpoint whether one systematic is the cause or some other systematic. So temperature variation, or a difference in the neutron background from radioactive decays near the source, or other things. So that is all I have to say. But I have my doubts that the result is genuine, mainly because I have never been able to observe the original starting distribution that they do analysis with. But okay, 10 years have passed, more than 10 years, and so. Well, I have to pay respect to my collaborators in Dama Libra. Probably they have done a good job after all. So it remains a puzzle, yes.
No, thank you very much, Tommaso, for your availability. Okay.
All right. So have fun with your school, and good luck to all.
So we have now a break until